Assalamualaikum warahmatullahi wabarakatuh and hi. In this video, we will learn about transient heat conduction. In transient heat conduction, time becomes one of the variable in our solution. This typically arises when boundary conditions within the system is changing as a function of time. This is the heat equation for one-dimensional constant properties. If we could solve this equation, we will get temperature in the function of x and time. But it's rather difficult to solve this equation when time becomes one of the variables. Luckily, we have a simpler model to get the same result out of this equation. This is called Lamb heat capacity model. Lamb heat capacity model is used in Lamb system analysis, which provides great simplification in certain classes of heat transfer problems without much sacrifice from accuracy. Now let's consider a body of arbitrary shape of mass m, volume V, surface area A subscript S, density ρ, and specific heat capacity C subscript P, initially at a uniform temperature of T subscript I. At time t equals 0, the body is placed into a medium at temperature T ambient, and heat transfer takes place between the body and its environment with a heat transfer coefficient h. For the sake of discussion, we assume that T infinity is greater than Ti, but the analysis is equally valid for the opposite case. We assume Lamb system analysis to be applicable so that the temperature remains uniform within the body at all times and changes with only time. So we know that the temperature of the object does not change or does not vary at any position, but it's only vary at given time. And now we are not going to solve the differential equation, but instead we're going to write the energy balance for the object, which will look like this, that we have learned before this in the previous chapter. So we know that there is no heat transfer out of the body and there is no heat generated within the body. So within the differential time interval dt, the temperature of the body rises by a differential amount dt at energy balance of the solid for the time interval dt can be expressed as heat transfer into the body during dt equal the increase in the heat energy or in the energy of the body during dt. Or in terms of equation, h a subscript s T ambient minus T dt equal mcp dt. And we know that m is equal rho v and dt is equal dt minus T ambient, which T ambient is constant. And now we can rearrange the equation to become like this. Now, if we integrate this equation from t equals 0, at which t equal Ti, to any time at which t equal Tt, it will give ln Tt minus T ambient over Ti minus T ambient equal minus HAS over rho VCPT. Taking the exponential of both sides, we will get Tt minus T ambient over Ti minus T ambient equal exponential of HAS over rho VCPT. And now we have this solution. What we can learn from this solution is that this solution enables us to determine the temperature of a body at time t, or alternatively the time t required for the temperature to reach a specified value of temperature. And the temperature of a body approaches the ambient temperature exponentially. And if we take B equal HAS over rho VCP and we sketch a graph like this, we can understand that if the bigger the B, the quicker it will reach ambient temperature. The quicker the body will reach ambient temperature. And once the temperature at time t is available, the rate of convection heat transfer between the body and its environment at that time can be determined from Newton's law of cooling. The total amount of heat transfer between the body and the surrounding medium over the time interval t equals 0 to t is simply the change in the energy content of the body. And the amount of heat transfer reaches its upper limit when the body reaches the surrounding temperature. Therefore, the maximum heat transfer between the body and its surrounding can be calculated from this equation. However, lump system analysis is not applicable all of the time. Lump heat capacity model only can be used when a dimensionless number called Biot number is less than 0.10. Biot number can be calculated using this equation. Bi equal HLC over K. H is the heat transfer coefficient, K is the heat conductivity of the object, and LC is the characteristic length, which can be calculated from V over AS. When a solid body is being heated by a hotter fluid surrounding it, heat is first convected to the body and subsequently conducted within the body. So the Biot number is the ratio of the heat convection, or the ratio of the internal resistance of a body to heat conduction to its external resistance to heat convection. Therefore, a small Biot number represents small resistance to heat conduction, and thus small temperature gradients within the body. Lump system analysis assumes a uniform temperature distribution throughout the body, which is the case only when the thermal resistance of the body to heat conduction is equal to 0. Thus, lump system analysis is exact when Biot number equal to 0 and approximate when Biot number is greater than 0. Of course, the smaller the Biot number, the more accurate the lump system analysis. Then, now let's look into this example. Metal plates with a thickness of 2 cm exiting an oven are conveyed through a 10-meter long cooling chamber at a speed of 4 cm per second. The plates enter the cooling chamber at an initial temperature of 700 degrees C. The air temperature in the cooling chamber is 15 degrees C, and the plates are cooled with blowing air, and the convection heat transfer coefficient is given as a function of the air velocity, H equal 33 V power of E 0.8, where H is in watt per meter squared Kelvin and V is in meter per second. To prevent any incident of thermal burn, it is necessary to design the cooling process such that the plates exit the cooling chamber at a relatively safe temperature of 50 degrees C or less. evaluate whether this case can be solved using a lumped system or not if the temperature of the plates exiting the cooling chamber is at 50 degrees C. In this example, the properties of the metal plates is also given. Before we can solve this problem, there are a few important assumptions. Number one, the thermal properties of metal plates are assumed to be constant. Convection heat transfer coefficient is uniform and heat transfer by radiation is negligible. So in order to know whether this case can be solved using lump heat capacity model or not, we have to calculate the Biot number and make sure that the Biot number is less than 0.1. And we know that Biot number equal H, or heat transfer coefficient, or convection heat transfer coefficient, multiplied by LC over conductivity of the metal plate. The characteristic length LC can be calculated using LC equal V over AS, and we can calculate LC using the information that given in the question, and we will get L subscript C, or the characteristic length of this metal plate, is equal to 10 millimeters. And then we also have to know we have the value of K, but we don't have the value of H. The K conductivity is given in the question, but H is given in the function of velocity, or the air velocity, which equal 33 V power of 0.8. But we don't know the velocity of air. So what we have to do now is we have to calculate the velocity of air. Using the lump system analysis, we know this equation. And from this equation, we know that B is equal HAS over rho CPV. Or we can rearrange this equation, B equal H over rho Cp LC. Or in other word, B is equal 33 V air power of 0.8 over rho Cp LC. And if we plug in all informations that we got from question, we will get this equation. But we still not solve the velocity of air yet. So the duration of cooling can be determined from the cooling chamber length and the speed of the plates. So T equal 10 meter over 0.04 meter per second, which equal 250 seconds. And we know that B is equal minus 1 over T ln T minus T ambient over Ti minus T ambient. And we know Tt, and we know Ti, and also we know T ambient. And we just calculated T. So we can calculate the value of B using those values, and we will get B is equal 0.0119. Unit is 1 over second. Now, the air velocity and convection heat transfer coefficient is necessary to cool the plates to 50 degrees C as they exit the cooling chamber. So we know that B is equal 33 V air power of 0.8 over rho Cp LC, which equal to 0.01195 second minus 1 power of minus 1. And we can solve V air using this equation. We just rearrange the equation to get V air equal 15.3 meter per second. And now we can solve H equal 333 V air power of 0.8, and we have the value of V air. We just plug in inside this equation. We will get H equal 293 watt per meter squared Kelvin. Now we can calculate Biot number. Biot number is equal HLC over K. So we got H, we got LC, and we got K. We know we can calculate Biot number, which will give the answer is 0.0163, which of course less than 0.1. So in conclusion, Biot number is less than 0.1 for this case, which means that we can use lump system analysis to solve this problem.